So starting from this week, we're going to talk about some techniques which are for solving the hard problems. The first one is this, approximation. Approximation is for dealing with the hard problems, not the undecidables, but some like the NP-complete problems. So to get around NPC, scientists would usually do one of the following. First, if n is small, then there's no big deal. Even exponential complexity is okay, right? For example, if n is only something like 10, so what's the big deal, right? Or in another case, if the general problem is hard, but some special cases are simpler, if by putting more constraints to the problem, we can then solve it in polynomial time, then we just concentrate on those cases. I mean, if we cannot solve for all the cases, at least we can solve some. And the third one is, if finding the real optimal solution takes too much time, let's find one that is sufficiently good. So to find near optimal solutions in polynomial time. And that is the main target of approximation. Notice that there's a difference between heuristics and approximations. When we use the word heuristic, it's also about obtaining a near optimal solution, right? But we will be concentrating on the method, not on the quality of the solution. For example, we may use greedy method as a kind of heuristic method to obtain a solution that is sufficiently good, but we don't know about how good is sufficiently good. On the other hand, when we discuss approximations, we do care about how close it is to the real optimum. So basically, when we do approximation, we will keep in mind this approximation ratio. We say an algorithm has an approximation ratio of rho of n if for any input of size n, the cost c of the solution produced by the algorithm is within a factor of rho of n of the cost c star of an optimal solution. So we have this inequality. And if an algorithm achieves the approximation ratio of rho of n, we call it a rho of n approximation algorithm. What does that mean? For example, if we are asked to find some minimum C star, that is the real optimum solution, but instead we can only find some approximation value C, which must be a little bit larger than this C star, because C star is supposed to be the minimum, all right? And if we can prove that our approximation C is at most, say for example, 1.1 times C star, then we say that this approximation ratio is 1.1, which is just C over C star. If C star is the maximum, then it will be the other way around. If our algorithm guarantees that we can always obtain solutions with this ratio, then this algorithm is called a, for example, 1.1 approximation algorithm. Another thing is an approximation scheme. An approximation scheme for an optimization problem is an approximation algorithm that takes as input not only an instance of the problem, but also a value epsilon, which is positive, such that for any fixed epsilon, the scheme is a 1 plus epsilon approximation algorithm. And we say that an approximation scheme is a polynomial time approximation scheme called pitas. If for any fixed positive epsilon, the scheme runs in time polynomial in the size n of its input instance. So it looks like if we can find a pitas, we can just let this epsilon get smaller and smaller and eventually tend to 0, can we? So does it mean that we can actually obtain the solution in polynomial time? Well, there's no free lunch. Okay, usually the complexity of a pitas would look like this, something like this. So you see that as epsilon tends to 0, it is polynomial, alright, but it will still go infinitely bad, right? However, it will look a little bit better if we have a complexity like this. Still, as epsilon tends to 0, it goes to infinity, but with a much slower pace, right? And this kind of scheme is called a fully polynomial time approximation scheme, or say F pitas. Fully means that if we look at complexity as a function of both n and 1 over epsilon, they are both polynomials. This is 1 over epsilon. Take it as a whole variable. This is something squared, and this is n cubed. They are both polynomials, all right? And that's what this fully means. Then we're going to check several famous problems that are solved by approximations.